Oh, sorry, I was on mute. Sorry about it. So I was saying that if there is any confusion in, last lecture, then you can just let me know. Hi, Prankush. Hi, Shiva. Hi, Kavya. Hello, Aditya. Hi, Devesh. Hi, Aditya. Okay. So now let's get started, right? Hello, Gaurav. Hi, Hitesh. Okay. So today we are going to see something like the previous lecture itself, which is that the row space and left null space. I mean, in last lecture, do you remember what was the topic? Do you remember the topic name? Can anyone tell me quickly what was the spaces that we have seen in the previous lecture? Okay. That was column space and null space. Yes. So this row space and left null space are just like that. I mean, basically these spaces are typically defined for, you can say A transpose, which means row space. Okay. So row space and left null space. Basically, I will say that row space of, okay, row space of A is as good as saying column space of A transpose. Okay. Similarly, you will get to know this in just a while, but I'm just writing it that left null space, okay, left null space of A is same as null space of A transpose. Okay. Okay. We will see that what do I mean by that. And also, do you remember I was talking about that? Okay, this topic is a favorite topic of Gilbert Stein, Professor Gilbert Stein. Do you remember? So I told you that there's a 5 minute interview. So I have added that link in the course itself. If you want, you can just watch that 5 minute interview. Okay, cool. Now let's just get started with the row space and left null space. So let's just see that what do I mean by that. So let's just take this matrix and let's just see that what is the row space of this A. Okay, suppose this is A. Then my question is that what is the row space of A? Okay, this is my question. Okay, now let's just understand that what could be the row space. Row space means I can say that okay, you can just tell me the basis vector and I will just get convinced that okay, this is the row space. Okay, if you want, you can just tell me the basis vectors. So what are the basis vectors of the row space? Let's just see. Let's just see. See here that I will say that for this matrix, okay, the row space is nothing but the space spanned by the rows of A. So I will say this is same as space spanned by the rows of A. Okay, which means I can say this is same as span of this 1 1 and 0 0. It doesn't really matter you are writing that in the column form or you're writing in the vector form. It doesn't really matter. Okay, I mean, if you want, you can write like this also, which is okay. Okay, I mean 1 1 0 0. Okay. So by the way, is this definition okay to everyone? That this is the space that is spanned by rows of this matrix, right? Now, if I ask you the next question, which is that what are the basis vectors? Okay. So if I ask you that what are the basis vectors of the row space, then what is your answer? What are the basis vectors of row space? Then you will say that answer is, should I be writing the basis vectors? Okay, just let me know. Should I be writing like this? Is this the answer? Tell me. Or this is the only answer. Just let me know. Which one? Let's suppose this is option A. Let's suppose this is option B. Okay, you can just tell me A, B, or first, second, whatever, right? Yes. So Sonam, the architect, and other people, Aditya, everyone is saying that option B is the answer. Okay, okay, great. Yes, option B is the answer because this is not even linearly independent. So basis by default, okay, I mean, basis have to be has to be the linearly independent. Actually, the 0 0 doesn't contribute anything, so it's no point in including that in the basis vectors. Okay, so I will say this is, I will say like this. I mean, this is basically wrong. Okay, this is correct. So finally, I will just remove this. Okay, so these are the basis vectors. Okay. Yes. So Anam is saying that option A is linearly dependent. Yes. Right. So it was linearly dependent. Yes, that's true. Now let me ask you another thing, which is going to be little more interesting. Let's suppose this is given to me. Let's perform some elementary row operation. Okay. So let's perform some elementary row operation. Maybe you can perform R2 gives R1 plus R2 or R2 plus R1, whatever. Okay. So now what will the matrix after that? 1 1 1 1, isn't it? Now you tell me, have we changed the row space? Have we changed the basis vectors of row space or the row space? Is is basis is changed now? I mean, whatever is basis changed now? What do you think? No, right? So see, this is also very common sense in the sense that if you have some matrix, okay, if you have some matrix, let's suppose this is one row, this is another row, this is another row, okay. Let's suppose these are the three rows or whatever number of the rows, and suppose you perform elementary row operations. Okay, let's suppose you perform elementary row operations. Now whatever matrix we are getting, it will be the combination of these rows only, right? I mean, see, in the elementary row operation, do we lose any row? Can I say that is this a valid elementary row operation? Tell me कि हटाई दो कोई रो को. Is this a valid elementary row operation? Tell me. No, right? So it is invalid elementary row operation. Okay, just tell me, is this valid or not? Okay, just answer me, is this valid or not? Is this valid? What do you think? No. Do you have you seen my lectures, like previous lectures? Okay, so from that you might be able to recall that if we are using R2, then R2 must be here. Do you recall that R2 must be here, right? So that's why this is also not valid, right? This is not valid elementary row operation. ठीक है, ये समझ में आया? So now you know that what are the valid and what are the invalid elementary row operations. So do we lose any row in the elementary row operation? This is my question. Do we lose, okay, कोई particular row को can I just say that okay, R2 is no more there? It's not true, right? I mean, the number of rows that we are having, I mean, the integrity is there, which means if we are having, let's suppose, three linearly independent rows, or let's suppose two linearly independent rows, then after the elementary row operations, the number of independent rows are same, so we do not, technically we do not lose, right? Is this okay to everyone? In other words, I can say that let's suppose you have A. Okay, let's suppose you have A, and then you got some matrix which is maybe R or something. Okay, after after elementary row operations, let's suppose you have got R. Okay, this is after elementary row operations. This is, let's suppose, elementary. Now you just tell me, can we get back? Can we get back A? Can we get back A using R? Is this possible? What do you think? What do you think? Yes, right? Yes. So yes, we can apply the reverse operations. It means that अगर कहीं पे ऐसा किया है R1 gives let's suppose C into R1, then I will divide, right? If I have done something like this, R1 gives R1 plus R2, which means I have added these two rows. Okay, I've got this particular first row using the addition of these two rows. Okay, then I can do one thing. R1 minus R2 I can do. Then I will be getting R1 again, right? So basically, in whatever way we have done, we can just apply the reverse operations, and then we can get that particular matrix that we started with, right? Is this okay to everyone? So we can just apply the same number of operations, and I mean, in the reverse form. It means if it is plus, then maybe minus. If it is multiply, then maybe divide or something like that, right? So I can say we can apply reverse operations. Is this fine to everyone? Let me know. Is this fine? Yeah, so basically, whatever the matrix R you are having here, right? You will be getting the same matrix A. Okay, you can get the same matrix A. So I mean, you say that you will be getting all the rows back, or you can get all the columns back. It's fine. I mean, you will be getting the same matrix A. Okay. Now now, so what I'm trying to say here is that you have some matrix A, and then you apply the elementary row operations. Then you are getting some matrix R, right? So basically this R in whatever way we have got, this is having the same number of linearly independent rows, right? And we are not also losing any row. It means that the space that is spent here, it is the same space that is spent here. See, what do I mean by saying that? If we have if we have, let's suppose, some rows, okay, one, two, three, okay. Now, if you say that, okay, let me replace this particular row with the summation of these two rows, okay, do you think the span will change? Which means if I say that span of UVW, then can I not say it is same as span of span of U plus V and W? What do you think? See, because see, whatever they are spanning, it will also span, right? Because they can also, whatever it can produce, they can also produce this, right? Why? Because first, if you're not very much convinced, then first you can produce this. I mean, from here U plus B. First you can take this linear combination, and you can produce these three vectors, and then obviously whatever they can produce, you can always produce this, right? So basically the span is same. So what I'm trying to say here is that if you apply the elementary row operations, right? If you apply the elementary row operations, you are adding, subtracting, or whatever you are doing, you are not losing any row, right? So basically the span here and the span after the elementary row operation is same. Okay. So the span means the column space. So what I'm trying to say here is that the row space. The row space doesn't change after the elementary row operations. Okay. So which is written here, the elementary row operation do not alter the row space. Okay. So for example, I think that is there. Yeah. For example, that a matrix and its echelon form have the same row space. The pivot of an echelon form is linearly independent. Okay, these are the linearly independent rows. Pivot row of an echelon form span of the row space of the original matrix. Okay, is this true for the column space? If I say the pivot columns, if I write the columns here, and if I write the column space, is this true for the column space, that pivot columns form the column space of the original matrix? No, right? It is not true for the column space. We have seen this in the previous class. The dimension of the row space is given by the number of pivot rows. Yes, the dimension does not exceed the total row count, obviously, right? So, I mean, it is very straightforward also to see that, okay, the row space doesn't change. If you have the elementary row operations, row space doesn't change. Like for example, if you have this matrix and then you do, let's suppose, so basically the row space consists of all the linear combination of this, right? Or these two rows. Thus, it is a span of this. If we identify the row vectors, that will point xy. So basically it will be just 1 1 k into 1 1. So basically this is the row space. Okay, it is just a line. Okay, row space of this is just a line. Understood? Okay. Now let's just find the basis of row space for this particular matrix. Find a basis for this row space. Can you do that? So let's just do one thing. Let's first reduce it to the equivalent form. So suppose I'm getting this. Okay. Suppose I'm getting this. Now, can you tell me the basis here? Let's suppose this is let's suppose C1. Sorry, R1 R2. Let's suppose this is R1. And this is R2. Okay. This is R3, R4, and R5. So this is the pivot element, I think, right? This is the pivot element. This is the pivot element. This is the pivot element, right? These are the three pivot element. Now, can you tell me the basis? Yeah, R1, R2, R3, right? So R1, R2, R3 is the basis. Let's suppose I call it, I call this some row number. Can you tell me the notation? What notation I can use here? A1 generally I like to denote with the columns. Maybe what can I say? Okay, let's call it AR. Okay, AR. Okay, I don't know. Maybe you can call it AR1, AR2, AR3, AR4, AR5. Now, can you tell me the row space? Can I say the row space is also AR1, AR2, AR3, and also R1, R2, R3, isn't it? So you can say the row space actually doesn't get changed. So that's why you can say that row space is actually equal to okay. Now let's suppose in the same question I ask you the column space. So can you say the column space is basically these three columns? No, right? So the column space, let's suppose this is C1, this is C2, then it is not the case, right? It should be A1, A2, and A4, right? Column space should be A1, A2, and A4. Okay. So let me also write that. Column space of A equal to span of A1, A2, A4, which is not equal to span of, let's suppose this is C1, C2, right? And this is A1, A2, A1, A2, like this, which is not equal to span of C1, C2, C4. Okay. 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 So let's just do this question, maybe the next question. Okay, before the next question, I think they mentioned the column space also for some example metrics. And now the column space of this is basically just a 1 0, right? And now they're saying elementary row operation affect the column space, which we have seen in the previous class itself. So generally a matrix and its equivalent form have the different column space. Okay. However, since the row operations preserve the linear combination between the columns of the equivalent form and the original columns obey the same relation. Have you understood what does this mean? Have you understood? Let me know that the linear relationship between the columns remains same. Have you seen my lecture of row reduced equivalent form? Okay, there I have mentioned this thing. Okay, cool. Now let's see what is written here. The pivot columns of row reduced equivalent form are the linearly independent. So basically, we get to know that okay, these are the linearly independent, and then we get to know the column space of the original matrix, right? So the dimension of the column space is given a number of okay. The dimension does not exist the column count. Okay, that's okay. Now let's just see very interesting fact that you already know. Basically, the dimension of the row space, as you might be seeing here, is nothing but the number of number of pivot elements, right? So dimension of the row space is nothing but basically you will say this row and, or maybe I can write it here. See, you will say this row, and this row. These three rows form the row space. So it is nothing but dimension is nothing but number of the pivot elements. Dimension of row space is also number of pivot elements. Dimension of column space is also number of pivot element. Why? Because in the dimension it counts the number of basis vectors. So if I ask you the number of basis vectors here, then you will say that okay, this is the basis, this is basis. I mean, this is also a basis vector, right? So these are three. Similarly, for the column space, you will say these are the three vectors, right? These are the three vectors which are in the basis. Is this fine? So basically, the dimension of the row space and dimension of the column space is same, which is also called as, what do we call it? Rank. Yes. So it is also called as rank. So that you must have inferred till now. So basically, dimension of the row space and dimension of the column space is nothing but number of pivot elements. Basically, dimension of the row space is nothing but you can say, I mean, in the basis you are taking the all the linearly independent rows. In this basis you are taking all the linearly independent columns, and both are equal, right? Which are equal to number of pivot elements. So that's why the rank and everything is same. Okay. Now, for the definition, let's just talk about the last definition here from the four spaces, which is left null space. So what are the spaces that we have seen till now? One is column space, right, of A. Another one is row space of A. And what is the third space that we have seen till now? It is null space, right? Null space of A. Okay. So these are the three spaces we have seen till now. Now let's just see something new. Okay. Something new, which is called left null space of A. Okay. Left null space. So a new subspace, let's just see. So far we have seen or we've seen and discussed the three spaces of M cross N matrix: row space, column space, null space, right? Row space of A is as good as column space of A transpose. Is this okay to everyone? See, if you are saying this row space, I mean this row space, if you take the transpose of this, it will be the column space of A transpose, right? So row space of A is same as the column space of A transpose. Okay. And column space of A, null space of A. Okay, that's fine. Now let's just see the fourth space, which is left null space of A, which is also the null space of A transpose. So I will tell you that what does this mean. Okay, so today, I mean, we are going to see this particular space. So we add to these fourth space subspaces, which is similar to the null space. We call it left null space, and it's the null space of A transpose. So let's just see that what does this mean. Okay. So we define the left null space like this. I mean, left null space of A is same as left null space of A is same as null space of A transpose. Okay. This is just a definition. I will tell you that why we are calling it left null space. I will tell you that what does this left mean. Okay. I will tell you, don't worry. So by the way, what is the null space of A transpose? It is nothing but all such vectors, you can say, which gives equal to 0, isn't it? So all such vectors which give this A transpose to be 0. So this is called null space of A transpose. We also call it left null space of A or A transpose. Can you tell me? Let me use by here. So we also call it left null space of A. Okay. Now let's just see that why we are calling it left null space. See, it is a null space of A transpose, that I agree, which means all such vectors which give you something like this. If you take the transpose both side, okay, then it will be Y transpose A equal to 0, isn't it? So it is just like the left of it, okay? In the left of it, we are having the vector. So that's why we call it left null space. Is this okay to everyone? So as you can see here, that thus the term left null space is there, because it can be equivalently viewed like this. Okay, so you can understand like this. So basically if you are having just like this, it is a null space. And if you are having in the left, if you are having, okay, don't worry about the transpose and all. This is just to adjust the dimensions. Okay, so don't worry about the transpose and all. So if you are having on the left of it, we call it left null space. Is this fine to everyone? Why we are calling it left null space of A? Or in other words, we call it null space of A transpose. Okay, so either you call it left null space of A or you call it null space of A transpose. Both are fine. Okay, now let's just see the dimensions. Okay, so Sonam is saying, sir, please repeat. See, this is the null space of A. Is this fine to everyone? And this is the null space of A transpose. Is this fine? Now, if we take the transpose here, okay, transpose here, you will be getting by transpose A equal to 0. So the null space of A transpose, we also call it left null space of A. Okay, left null space, because just because it is in the left. It is by the definition. I mean, that's how scientist has defined that. Okay, mathematician has defined like this, that we also call it left null space of A. Okay, cool. So I hope little bit you might have understood, but don't worry. You will get to understand that more. Okay, you will get to understand more. Okay. So now suppose A is M cross N matrix. Okay. Suppose A is M cross N matrix. Can you tell me the dimension of the column space? It is the rank, right? Let's suppose rank is R. Similarly, dimension of the row space, dimension of row space, which is the column space of A transpose, it is also R, right? What is the dimension of the null space? Can anyone tell me? If A is M cross N matrix, can anyone tell me what is the dimension of null space? Yes. So Hers, Diksha, Devis, everyone is saying N minus R. Why it is N minus R? Because of rank nullity theorem, right? Do you remember rank nullity theorem? What does this says? That whatever is the rank of A, which is R, and the nullity of A, which is the null space dimension, it should be the total number of columns. Okay, so total number of columns minus the rank, it will be nullity or the null space of A. Now, can anyone tell me the dimension of the left null space? Okay, or maybe we also represent like this null space of A transpose. Can anyone tell me this? This is going to be interesting and also little tricky. Okay, so what is this? This is, yeah, Diksha and Aditya has given correct answer. So this is M minus R. Let me just tell you why. See, let's just see with perspective of A transpose. So for A transpose, what is the column space dimension? For A transpose, what is the column space dimension? It is R, right? It is R because this is the row space of A, and you can say it is R. So for A transpose, you can say for A transpose, right? Column space, you can say dimension of the column space plus dimension of null space should be number of columns. Can you tell me number of columns here? This is n cross m matrix. It should be m because m is number of columns, right? It is the number of columns. Is this equation fine to everyone? With respect to A transpose, right? With respect to A transpose, I'm saying dimension of the column space plus dimension of null space for any matrix equal to number of columns. And it so happens that here the number of columns is small m, right? Okay. So I hope that is fine. That number of columns are here, small m. Now let's just see that what is the dimension of column space? It is same as the dimension of the row space of A, right? Which is same as, I mean, you can also say it is the rank of the A transpose, which is same as the rank of A, right? So this is the rank of A transpose or rank of A. So it is just a R, right? Plus, this is what we are interested to find out, dimension of the null space of A transpose. Okay, so dimension of null space of A transpose, right? Which is equal to M. So this particular number, dimension of null space is A transpose, is coming out to be M minus R. Let me know if that is fine. which is same as the left null space. Okay, so again and again I'm telling you that left null space is nothing but null space of A transpose. Okay, so see here that these are the dimensions. Okay, this is M minus R. This is little interesting. So see, ideally, how many spaces are there? Only two spaces. What are those two spaces? Column space and null space, which are related by which, what theorem? Space. These two spaces are related by which theorem? Rank nullity theorem. Okay, ideally you can say there are only two spaces. Okay, and these two spaces are tightly bound. Okay, you can say these two spaces are related by rank nullity theorem, right? Is this fine to everyone? Okay. Now, if you talk about other spaces, then you can say you can talk about the other spaces in terms of A transpose also. So A transpose, column space and null space are nothing but row space of A and left null space of A. Okay. So ideally, these are only two. Okay. For A, you can say there are only two. But we have defined two more with I mean, using the help of A transpose, you can say. Okay. So column space and null space are only two which are driving factor, but we have two more spaces that we can define in terms of A transpose also. But if you want to define that in terms of A, then also you can say it is a row space of A, it is a left null space of A. Okay. So maybe we can see one question where we can do all of these spaces so that it get more clear. Okay. This question I have taken from University of Otaha. Let's just see this question what they are trying to say. So they're saying find the basis for each of the four subspaces associated with A. Okay. So with this A, what are the bases associated for each of the subspaces? So what are the subspaces? I think column space is one of the space, subspace, and null space is another subspace, and row space is another subspace, and left null space, right? Okay. Is this fine to everyone? Now, let's just see what is the basis for the column space. I think this is easy. Can you tell me what is the basis for the column space? Anyone? Yes. So this is just the first column, right? Which is 1, 2. So I think this is easy to find out the basis for the column space because the columns are linearly dependent. You can see. Okay. So easily you can say that, okay, this is something like this. What is the basis for the row space? Or let's just first find out the basis for the null space. How many how many basis vectors will be there in the null space? How many bases? What is the dimension of the null space? What will the dimension of the null space? Can you tell me? I think it will be 2, right? Because there are two free variables, right? Okay. So maybe I can write it here. Just apply some elementary row operation first. I think I can say R2, R2 minus 2R1, right? And then A will be 1, 2, 4, 0, 0, 0, right? And then I can have 0, 0 also. I mean A, B. Okay. Now, the this is the only pivot variable. So the free variables are x and y. Oh, sorry, y and z. So y will be, you can say s, and z will be, you can say t, right? So what is the value of x that you are getting? I think x will be minus 2s minus 4t, right? So what is the vector that you are getting? Minus 2s minus 4t, s and t. Okay. This is the solution of this matrix. I mean, after the row reduce. Is this the same solution of this? Tell me. This is the solution of this reduced form. Is this the same solution of this A? Yes, right? Okay, do you remember the solutions doesn't change, right? So the null space doesn't change actually. So this is the null space that we are getting for A. I hope you can decompose and then you can write it. Maybe I can just show you. Okay. Yeah. So this is the null space. Okay. I think that's easy. And the column space is just 1, 2, right? I think most of you have pointed out it correctly that this is the column space. Row space is, can you find out the row space? It is 1 to 0. Sorry, 1 to 4. Okay. So row space is just 1 to 4. Okay, this is A. Okay, A is already there. Give it. Okay. So for this given matrix, I think just the only space that is left is left null space. Okay. So I am saying here is that the solution of this A, okay, I mean solution, whatever solve this AX equal to 0, okay, and whatever solve this let's suppose RX equal to 0, are they same or different? Are they same or different? Tell me. This X here, if it is satisfying this R, then it will also satisfy this A. Okay. The solution set doesn't change. I mean, that's how we actually solve for X equal to 0. So that's why I'm saying the null space also doesn't change with the elementary row operation. Okay. Null space also doesn't change. Okay. Now, what I'm saying here is that the last space that is remaining is left null space. Can anyone tell me how we can find out the left null space? What should be the first step to find out the left null space? Is to take transpose of the matrix, right? So let's just find out the left null space. See, if this is A, the very first step of the left null space is to find the transpose of this matrix. Now what you can do? Now you can find the solution of this. So what are the solutions of this? I think you can apply the elementary row operation and then you can make them 0, right? This is very easy to see. So I think you can make them 0. So it will be 1, 2, 0, 2, 4, sorry, 0, 0, 0, 0, right? Okay. Is this fine to everyone? Now you tell me what are the solutions? What is the free variable? I think y is the free variable. You can make it t or s, whatever. And then x will be minus 2t, right? So what is the decomposition that you're getting? Minus 2t and t. So the final answer is minus 2t and t. This is the, tell me this is what? Left null space, okay? Uh, minus 2 and 1. Is this fine to everyone? This is the left null space. Okay. So null space of A transpose is the left null space of A. So maybe you can see minus 2 and 1. Okay. This is the basis for the left null space. Understood? Great. So I think you understood that given this matrix, how to find all the spaces. Okay. Will you be finding any difficulty to find the basis for any of this space? Easy, right? If you want to find the basis for the row space, I think you use elementary. First of all, you do elementary row operation because it is needed for null space, it is needed for column space, it is needed for row space also. And if you want to find out the left null space, then take transpose and do the elementary row operation, right? Okay, let's solve more questions. Probably it will be more clear using the more questions. Let's solve more questions now. Okay, just tell me this particular question. If the null space of A is in Rn, then the column space of A is in, suppose A is, so is Rn. Okay. So the null space is actually Rn. Let's suppose A is M cross N matrix. Then the column space of A is, what do you think? Just think about it. Let me give you the hint. Oh, sorry, not the hint. Let me write some options. Okay. Let me write some options. So let's suppose option A, this is also Rn. Option B, This is Rm. Option C, this is just, let's suppose zero vector. Option D, this is R n minus m. Okay. So tell me which one is correct. So they are saying left null space. Okay. So what do they mean by that left null space? It means that null space of A transpose. Okay. Null space. Sorry, then the matrix cannot be in M cross N, I think. Null space of A transpose, if that is having dimension of that is basically it is Rn. Okay. It is Rn. Okay. This is interesting. If it is Rn, actually the dimension, just give me a second. Let me just check the dimension of the matrix. Okay. So actually the dimension I forgot to, I think, write it. Okay. It is n cross n matrix. So it is a square matrix in the question. I just verified it from the source link. So on this link, they are saying that let A be n cross n matrix. Okay. So let me just put it. Okay. Now you tell me, if the null space of A transpose is Rn, okay, which means what you can say about the rank of this A transpose or the rank of A, it must be zero, right? See, the dimension of this null space or the nullity is, you can say here, it is n. So which means the rank of A transpose must be zero. Okay, rank of A transpose must be zero, isn't it? Is this fine to everyone? Because rank plus nullity must be n. So the nullity of A transpose is n, right? If the nullity of A transpose is n, and rank plus nullity both must be of A transpose, I'm talking. Let's not get confused with A. We will come to A in a while. But for A transpose, is this okay? Rank of A transpose is zero. So this is same as rank of A, right? So rank of A is zero. And in what case rank can be zero? Can you tell me? In what case rank can be zero? Only when it is a zero matrix, right? Rank can be zero only when it is a zero matrix. Okay. Otherwise, rank cannot be zero. So rank can be zero only when it is a zero matrix. So maybe I can write it. Rank of any matrix is zero only when it is a zero matrix. If it is a non-zero matrix, then rank cannot be zero. Okay. So A transpose or A is the zero matrix. So that is why if I ask you the column space, then it is just zero, right? Because it is a zero matrix. Then it will be zero. Okay. Okay. Now let's just do more questions. What they are saying. Verify that all the vectors in your basis of the null space are orthogonal to all the vectors in your basis of row space. So they are saying that you have row space, you have null space. You take any vector in the or any basis vector in the null space or any basis vector in the row space. They are orthogonal to each other. Can you verify this? Can you verify? See, see. Let me just give you the example. Let's suppose it is the null space. Okay, it is giving you the zero. It is giving you the zero, right? Let's suppose. Now, how you get zero? You multiply this row with and you multiply this column, and then you get this zero, isn't it? Tell me. So basically, this row is is orthogonal to this null, some vector in the null space, right? So even if you write the basis vectors, which means even if you have the reduced form, okay, if it is a reduced form, then you directly have the basis vectors here, right? So if it is a reduced form, then also it is true. You have the reduced form here, and then you have something from the null space, right? You have something from the null space. Then this and this are orthogonal, isn't it? So row space and the null space are orthogonal to each other. Let me just tell you from the examples that we have done. See, row and null space. See, this is the row space 1 to 4, right? This is the row space of this matrix 1 to 4. Let's just verify. Is the 1 to 4 orthogonal to this? Tell me. If you have 1 to 4, if you multiply 1, do the dot product, it is minus 2 plus 2 into 0. Isn't it 0? It is minus 4, 0, and then plus 4. Isn't it 0? Right? So this is the basis from the row space. Basis of row space. Okay. The basis of row space is orthogonal to null space basically, and not just basis. If basis is orthogonal, then obviously the every other vector is orthogonal. Why? See see here, that let's suppose you have some vector, right? Some vector v that must be able to represented using the basis vectors, because basis vector can represent all the vectors. Okay, so let's suppose the basis vectors are b1, b2, b3. Let's suppose there is some vector un, okay, which is a null space vector. Since we know that b1, b2, b3 are the basis vectors of row space, these are the basis of row space. Okay, now this vector is some arbitrary vector from the row space. Now what I'm saying here is that if this basis is orthogonal to this un, don't you think this v and un dot product will also be zero? क्योंकि क्योंकि un into b1 it will be 0. 0 plus 0 plus 0 is 0, right? So this is same as c1 b1 and multiplication with un c2 b2 un c3 b3 un. So it is nothing but 0 plus 0 plus 0. It is nothing but 0 vector, right? So basically, if this vector is orthogonal, if the null space is orthogonal to the basis vectors, then obviously it is orthogonal to every other vector, right? Any vector. So in general, you can say any row, any vector in the row space, basically any vector in the row space is orthogonal to any vector in the null space. Okay. So let me write it here. Any vector in row space is orthogonal to any vector in null space, because that's how null space is defined actually, right? Null space is defined like this only. This vector into this vector and will give you the zero. That's how null space is defined. Okay. What about ax equal to b means? No, this is not system of linear equation. The spaces are defined for A. Okay. All of these spaces are for A. This is not for ax equal to 0 or ax equal to b or something. Okay. Just drop the system of linear equation from your mind. Okay. The spaces are defined for matrix A, not for the system of linear equation of something. Okay. All of these spaces I'm talking about are for A. Okay. Just drop this system of linear equation from your mind for now. Okay. Understood, right? So now let's just do the next question. What they're saying. There is a 3 cross 4 matrix whose null space is a plane, whose column space is a line. Is this possible? Is this possible? Tell me. No, all of these spaces are for any matrix, any arbitrary matrix A. It need not to be square matrix or something. So what they're saying that that 3 cross 4 matrix is there. Null space is a plane. It means the dimension of null space is nullity is 2, right? And column space is a line, which means rank is 1. Is the summation is giving you the number of columns here? Tell me. No, right? So that's why it is false. False by rank theorem or rank nullity theorem. The dimension of the null space and the column space must be exactly 4. In the proposed scenario, the dimension would add to 3. Okay. Okay. No, you can take the transpose. Aditya is asking, we can't take the transpose for the rectangle matrix. You can take the transpose for any matrix. Need not to be the square matrix. Okay. Uh, Harsh is saying, sir, can't we call null space is a plane when dimension is 3? Generally, we call it hyperplane. Okay. So, generally, for the plane, we will be using 2D plane. Otherwise, it will be mentioned. Generally, we call for the 3D planes and these things, we call it hyperplane. Okay. If the plane is in 3D, we call it hyperplane. Okay. Now, let's just see this question, which is from MIT. So, what they are trying to say, a matrix A is given to you. What are the dimension of the 4 subspaces associated with this matrix A? Okay. They have A and B, something like this. Now they are saying this will of course depend on the value of A and B. You should distinguish all the different cases after doing the row operation. So you are getting something like this. Okay. You are getting something like this. So now they are saying, what if A equal to 2B? Then what are the dimension of all the spaces? If A is not equal to 2B, then what are the dimension of all the spaces? Okay. So this, and then A minus 2B is there. Now, if A equal to 2B, then what is the dimension of all the spaces? If A is not equal to 2B, then what is the dimension of all the spaces? Okay. Do you want to try this now or as an homework? Tell me. Answer is there on the next page. So you can do whatever way you like. So basically, they're asking you this thing, right? In both the cases. Okay. Okay. So you can try this as an homework, right? Is this okay? Answer is on the next page, and I feel you should do some practice. So that's why I'm giving you as an homework. Answer is already there on the next page. And by the way, this question I've taken from MIT. It's a good question. Just try this out. Okay. It will lead to some confidence that you are learning the things, right? So just try this out in both the cases. So if A equal to 2B, then what are these 4 answers? If A is not equal to 2B, then what are these 4 answers? Okay. Now again, there's a question from MIT, and I think this is almost same question, but they have something else. For A equal to B equal to 1, okay, give a basis for the column space, then also basis, is this also basis for R3? So they are saying if A and B are 1, then give the basis for the column space of A. Again, answer is on the next page. Okay, answer on the next page. You just try this also as an homework. Is this okay if you can try that also as an homework? Okay, because answer is already there on the next page. Okay. Now let's see this question. What they're saying: if m equal to n, then row space of A equal to column space. What do you think? They are not talking about the dimension. Okay, they are not talking about the dimension of the row space. They are saying the row space itself. See, let's take our example. This we have taken multiple times. So the m is n and the row space is I think 1 0. Sorry, the column space is 1 0. Row space is 1 1, right? So they are not same. I mean, for it is actually not true. For the square matrix, it is not like that. Row space and column space are the same. So I can say here is that here row space is 1 1, column space is 1 0, right? Obviously, they are not same. Okay, they have some other counter example, but that's fine. Let's see this question again. I have taken this question from MIT. Okay, let's see this question. What they're saying: the matrices A and minus A share the same four subspaces. Yeah, dimensions are always same. Okay, what about the dimension? Do you really need m equal to n? Do you really need m equal to n for the dimension to be same? No, right? Dimension of the row space and dimension of the column space are always same, which is the rank of the matrix. Okay. Now they are saying the matrix A and minus A share the same four subspaces. What do you think? It seems to be true, right? It is true actually, because see, whatever is the column space of this, right, or whatever space of this, you just need to multiply by the minus there. That is same, right? In fact, you can say, in general, you can say this is A and CA. C be any scalar, right? Share the same four spaces. What do you think? Is this also true or false? This is also true, right? Because whatever space of A is there and whatever space of C is there, it is just a multiplication of C, and you can always multiply by the C, right? In those basis vectors or something. Yeah, C C cannot be zero. Yeah, so non-zero. Non-zero. Okay. See, this is true. Okay, I mean they have proved it, but that's fine. Okay. Now let's just see this. If A and B share the same four spaces, then A is a multiple of B. Oh, nice. This is the reverse. See, if A is a multiple of B, then it is true. Then it is true. Okay. We have just seen that, okay, CA and A both share the same spaces. But now they're saying the reverse thing. If A and B share the same four spaces, now is this necessary that both are multiple of each other? What do you think? Is this necessary that both are multiple of each other? Just think about it. So for a hint, what you can do, just think about it. Take some matrix A whose column space itself the whole R2. Okay, column space should, let's suppose it is whole R2. Then what is the row space of that particular matrix? Let's suppose it is 2 cross 2 matrix. Okay, it is again R2. Let's take A as 2 cross 2 matrix. Okay, column space is R2, row space is R2. What will the null space? Obviously, it is 0. What is the left null space? It will also be 0 because row space is R2, so left null space is also 0. Okay. This is about A. You can take any random A. Tell me, can you have B which has no relation to A and still all of this are same? All of these spaces are same. Is this possible? That can we have a B? Just think about it. Which has no relation in terms of multiple, right? See, initially these things might not come to you, but as we go through, as we progress through, you will get to understand all of this very clearly, and then you will be able to produce and you will be able to come up with the examples. Okay. So just I'm building the things, right? Yeah, obviously any b, okay, any invertible b. You can have anything. It's like, for example, it is 1 2, let's suppose 2 3. It could be anything, right? It could be, let's suppose, 1 1 2 4, right? Is this multiple of this? I don't think so, right? So this is any b which is just invertible. If it is invertible, then obviously the rank is 2. If the rank is 2, then the column space is R2, row space is R2, null space is 0, left null space is 0, right? It also share the same, all the spaces same, but they are not having any relation to each other. Is this okay? Okay. So don't worry, you will also get to come up with the counter example or come up with the examples with the course, as the course progress. Okay. So you will get to understand row space, column space, these geometrically in the next lecture. So in the next lecture, I will relate all of these spaces geometrically, that how they're even related to each other. So then you will be able to understand all of this very nicely. Okay. So currently you might not be able to come up with the examples and counter examples, but later on, have some patience. Later on, you will get to know. I mean, you will get to come up with. Okay. So now let's just solve this question. What they are saying? I think that question you can solve as an homework, right? Is this fine? They're asking the dimensions of the spaces. So I think you can solve as an homework. Okay. If a vector v has dimension k, then okay, this is the true false question. If a vector v has dimension k, then any set of k linearly independent vector is a basis for v. What do you think? This is Aditya saying it is true. What do you think? Other people? Yes, this is also true, right? This is true. Yeah, Sonam, yes, everyone is saying this is true. Because see, if the dimension is k, then the basis vectors are k. There are k basis vectors. Then obviously, you pick any k linearly independent vectors, those will be the basis vectors, right? So that's why it is true. Okay. Now let's just do one tricky question. Okay, which is the prove that any arbitrary matrix A and B, for any arbitrary matrix A and B, the column space of A and B is subset of column space of A, which means if X is in column space of AB, then you need to prove that X is also in column space of A. This is little tricky. Let me just give you the hint here. If X is in column space of A, it means X can be represented as AB by, right? I mean, it is a, you can consider this as just one matrix. So basically, it is a linear combination of columns of AB. Basically, X is AB by. Is this fine to everyone? If X is in the column space, it must be having this form. Then you need to prove that X is also A into some Z, some vector Z. Okay. I think we just proved it, right? We just proved it. So if X is AB by, then obviously it is A into something also. Yeah, it is A into something. We just need to prove that it is A into something, A into some vector. Yeah, that is clearly visible. Is this fine to everyone? So what I'm saying here is that column space of AB is a subset of column space of A, which means if X is in column space of AB, then it is also in the column space of A, which means I want to prove that if X can be, okay, I'm just translating that into the equality. Okay, now either you write like this or you write like this, both are same. So I'm saying that if X is AB by, then it is A into something. Yeah, that is true. Or you, if you want to understand intuitively, then also you can understand. See, you can understand intuitively also. If X is, or you can say that linear combination of A, I mean, column space of AB is nothing but linear combination of columns of AB, right? These are the columns of AB. Let's suppose this is AB. Linear combination of columns of AB. If something can be linear combination of columns of AB, then it must be able to represent it using just a linear combination of columns of A, right? See how you got AB. All of this are nothing but, मतलब you can say this is the parent, right? ये इसी के तो बच्चे हैं, मतलब ये यहीं से तो आए हैं, ये वेक्टर इन तीनों से तो आया है, ये वेक्टर इन तीनों से तो आया है, ये वेक्टर इन तीनों से तो आया है, राइट? तो कुछ भी ये अगर प्रोड्यूस कर सकते हैं तो ये तो कर ही सकते हैं ना. Getting my point? If something can be represented as a linear combination of columns of AB, then obviously you can represent as a linear combination of columns of A. Are you getting intuitively also? Because all of this are nothing but the linear combination of columns of A itself. मतलब you have produced it using the linear combination of columns of A. Now I'm saying कि यहां से whatever you further produce, obviously you should be able to produce using this, right? So what do I mean by that? कि you started with A, which is something like this, okay, which is something like this. Then you have made some linear combination of columns of A, and you got, let's suppose, something like this. How you got it? Using the linear combination of columns of A, let's suppose, okay, which means out of these three you got this, out of these three you got this, out of these three you got this. Is this okay to everyone? That columns of AB are nothing but linear combination of columns of A. That's how we get AB, right? You know how to multiply two matrices? How many of you know that, okay, AX is nothing but columns of linear combination of columns of A, right? So similarly, AB is nothing but linear combination of columns of A, where this vector you will be getting by these three linear combination coefficients will be coming from this, the first vector of AB. Should I repeat it, or you already know this? See, this is A, this is B. And if you multiply these two matrices, let's suppose whatever the matrix you get, how you will be getting, just tell me. Let's suppose this is the first column A1, this is A2, this is A3. Okay. Now, how you will be getting this C? How you will be getting the third? Let's suppose this is, let's suppose, some B11, B1 or 21, V31. Okay. So what is the first column here? Can anyone tell me? It is nothing but the linear combination of these columns, right? A1, and the coefficients will be coming from here, plus V21 plus, is this fine to everyone? Let me know, right? So similarly, I can say this vector also is nothing but linear combination of columns of A, right? Which means this vector is also nothing but, let's suppose, this is B, first row, second column, second row, second, third row. Okay. So this particular vector is also similarly like this, right? You can say it is V12 A1 plus B22 A2 plus B32 A3, isn't it? So basically, these vectors are nothing but linear combination of columns of A. Is this fine to everyone? So in AB, these whatever vectors you get are nothing but linear combination of columns of A. अब ये जो कर सकते हैं, है ना, whatever you can produce from this, can't you produce from this also? Tell me. If X is in the column space of AB, then can't you say it is also in the column space of A? ये तो पेरेंट है ना, इसी ने तो इसको बनाया है. अब यहां से लीनियर कॉम्बिनेशन से जो भी आ रहा है, यू कैन ऑल्सो गेट इट फ्रॉम हेयर, isn't it? Let me know if you're getting it or not getting. Okay, just think about it, that you're getting something from this linear combination, so you can say you can also get the same thing from these linear combinations, right? Okay, that's what I'm trying to say. So in other words, obviously mathematically you can try to prove like this, that if x is in the column space, which means x is equal to AB by, then also it is A into something, right? Which means if it is a linear combination of columns of AB, then also you can get it from columns of A. Okay, that is for sure. Cool. Now let's just do one more tricky question. Okay, on the similar line, what they are saying, if B is invertible, then actually earlier we have proved, okay, earlier we have proved that column space of AB is actually a subset of column space of A. Now I'm saying that both column space are same if B is invertible. So basically A is nothing but, you can rewrite it like this. Okay. Now, can you say that column space of A, which is same as column space of A, B, B inverse? Okay. And now if you know, if these are the two matrices, right? Let's take it as a two matrices, right? Let's take it as two matrices. Then can you put a subsets here, subset sign here, and what should be what I should be writing here? Can anyone tell me? See, these are the two matrices. You drop one matrix, you pick another matrix, right? So you will be writing AB, right? AB. Because this is the first matrix. You just treat this as a one matrix. So uh, now what you are saying, that column space of A, which is same as column space of this, which is a subset of column space of AB, right? So we have proved other way also that column space of A is a subset of column space of AB, and it is column space of AB is subset of column space of A. I mean, in general, it is true, right? And for if B is invertible, then this is also true. So using this, can you say that both are equal? Actually, I want to give this as an homework. Okay. That's why I just made it very quick. So just try to do this again as an homework. Okay. Without seeing the solution. Solution is on the next page, but I want to do this as an homework. So that's why I did it. Quick hint. You just try this as an homework. Okay. Solution is there on the next page, but you just try this as an homework. Okay. And then all of this will make sense, that what is, why that is true, why that is not true. All of this will make sense after some while. Okay. I mean, currently we are seeing that as mathematically, but later on it will be so habitual that you will be understanding intuitively also. So for now, just take it as mathematically, that how to prove, how not to prove. Later on it will be very very intuitive also. Okay. Cool. So now we have covered just the definitions of four spaces. Okay, how to find the basis and all. We have covered all the mathematical things, like, okay, how to find the basis, what are the definitions. But there are something that are still pending about these four spaces, which makes these four spaces very beautiful. Okay, so we will keep on having lectures on the four spaces. I think there will be two or three lectures which will be required for these four spaces. And after those 2 3 lectures, it will be very much comfortable for you guys to understand all of these spaces, because all of these spaces, as I told you, are very very important for linear algebra. So that's why I'm spending so much time in that. And then we will be starting another topics, okay, from the linear algebra for gate D. I hope my pace is not too slow. If you think that it is slow or fast, you can just let me know over the Telegram. Okay, cool. So that's all for today. Thank you everyone. Thank you so much. Take care. Bye bye.